The horizon is indistinct. It does not separate cleanly from the earth below. Instead, it dissolves into a uniform gray, where sky and ground merge into a single, uncertain plane. There is no sharp boundary, no reliable reference, only a gradual fading of contrast. Below, the terrain stretches outward in muted tones, fields, sparse tree lines, shallow ridges. From altitude, it appears still, unchanging, but its details are already beginning to disappear. Inside the cockpit, the instruments are few: a magnetic compass, an altimeter, an airspeed indicator, basic engine gauges, the needle steady but imprecise. There is no artificial horizon, no reliable way to determine attitude when the outside world fades. The aircraft moves forward through it. It is no longer transparent. Cloud begins as a thin veil, then thickens. Visibility narrows. At first, the pilot maintains visual reference with the ground. Small corrections, minor adjustments. The flight continues as planned. Then, gradually, the ground disappears. There is no moment of sudden loss, no clear transition, only a subtle shift from partial visibility to none at all. The aircraft is now inside cloud. Without external reference, the body begins to misinterpret motion. The inner ear suggests stability, even as the aircraft slowly drifts from level flight. A slight bank develops, almost imperceptible. The compass responds slowly, its oscillations difficult to interpret in turbulence. The altimeter begins to unwind, not rapidly, not alarmingly, just enough to go unnoticed at first. The engine continues its steady rhythm. There is no indication of mechanical failure, no warning of imminent danger, only the absence of information. Outside, the cloud thickens into uniform opacity. There are no shapes, no shadows, no horizon. Inside, the cockpit becomes a space defined by uncertainty. In the early decades of aviation, this moment was not uncommon. Pilots flew primarily by sight. Navigation depended on landmarks, rivers, rail lines, roads. When those references vanished, there were few alternatives. Instruments existed, but they were limited, often unreliable, and not always trusted. Training reflected this reality. Flying without visual reference was not yet a standardized discipline. The concept of fully controlled instrument flight was still emerging, not yet widely adopted. Many pilots had little experience maintaining stable flight without the horizon. The aircraft continues forward. A slight descent becomes more pronounced. The bank angle increases incrementally, still subtle, still within a range that feels manageable. But without correction, it compounds. The airspeed rises. The nose lowers. There is still no external reference to confirm the change. In this environment, perception and reality diverge. The pilot may sense level flight. The instruments, limited as they are, suggest otherwise. But interpreting them requires training, discipline, and trust in abstract indications over physical sensation. In the 1920s and early 1930s, this conflict was unresolved. Many aircraft entered cloud with no clear method of safe exit. What follows is rarely abrupt. There is no single failure, no dramatic event, only a gradual progression, small deviations accumulating into instability. The aircraft ascends further. Terrain, still hidden beneath cloud, rises slowly to meet it. There is no warning system, no terrain awareness, no radio guidance, only altitude diminishing and time narrowing across the world. In the early decades of powered flight, variations of the sequence repeated over farmland, over forests, along coastlines obscured by fog, in mountainous regions where elevation changed faster than pilots could anticipate. Each incident appeared isolated, different aircraft, different crews, different locations, but the underlying structure was often the same. Limited instrumentation, inadequate training for instrument conditions, unpredictable weather, and a reliance on visual flight in environments where vision could be lost without warning. The aircraft continues its descent. At a certain point, recovery becomes unlikely, not because of a single irreversible moment, but because the margin for correction has been quietly consumed. The ground remains unseen until it is no longer distant. In early aviation, accidents were not always the result of dramatic failures. More often, they emerged from systems that had not yet matured, technology still in development, procedures still undefined, and environments not yet fully understood. This is where the story begins, not with a single crash, but with a pattern, a period in aviation history where progress outpaced protection, and where each accident contributed, incrementally, often at significant cost, to the knowledge that would later define safe flight. The end of the World War I left behind more than political realignment. It left behind aircraft, thousands of them, surplus machines, no longer needed for combat, now repurposed for a new kind of frontier. Alongside them, a generation of pilots emerged, men trained in urgency, accustomed to risk, and familiar with aircraft that were, by modern standards, incomplete. Aviation did not begin cautiously. It accelerated. Through the 1920s, flight transitioned from spectacle to utility. What had once been demonstrations at fairs and exhibitions became something more structured: mail routes, passenger services, cargo transport. The aircraft were evolving, but not uniformly. Designs varied widely. Materials differed. Engineering philosophies were still being tested in real time. Wood and fabric remained common. Fuselages were often constructed from timber frames, stretched with doped fabric to create aerodynamic surfaces. These materials were lightweight, easy to repair, and well understood by craftsmen. But they were also vulnerable to weather, to stress, and to time. Moisture weakened structural integrity. Temperature changes altered tension. Fatigue, though not yet fully understood, accumulated quietly. By the early 1930s, a transition had begun. Metal A-frames, stronger, more durable, and capable of supporting higher loads, started to replace earlier designs. Aircraft like the Ford Trimotor represented this shift. Corrugated metal skins, multiple engines for redundancy, and increased passenger capacity signaled a move toward reliability. But progress was uneven. For every advancement, there remained a parallel world of older aircraft still in operation. Airlines, often operating with narrow margins, continued to use what was available. Standardization had not yet taken hold. Cockpits reflected this diversity. Instrumentation varied not only between manufacturers, but sometimes between individual aircraft. There was no universal layout, no consistent system of interpretation. Pilots adapted to each machine as needed, often relying on familiarity rather than formal procedure. Navigation, in particular, remained primitive. Before the widespread adoption of radio-based systems, pilots navigated by dead reckoning, calculating position based on speed, time, and heading. Landmarks served as confirmation. Rivers, railways, coastlines. These features provided orientation, but only when visible. At night, or in poor weather, they disappeared. Some early radio navigation aids began to emerge in the late 1920s and 1930s. Low-frequency radio ranges transmitted directional signals that pilots could follow, but coverage was limited. Reliability was inconsistent. Interpretation required training that was not yet universal. Air traffic control, as a coordinated system, did not yet exist. Flights departed according to schedule, but once airborne, they operated largely independently. Communication with ground stations was sporadic. In many regions, non-existent. Separation between aircraft depended on timing, not real-time coordination. Weather forecasting added another layer of uncertainty. Meteorology was still developing as a science. Forecasts were broad, often inaccurate, and lacked the resolution needed for aviation. Pilots received general conditions before departure, but in-flight updates were rare. Storm systems developed faster than they could be tracked. Fog formed without warning. Icing conditions, particularly dangerous for early aircraft, were poorly understood. Ice accumulation altered wing shape, increased weight, and reduced lift. In aircraft without de-icing systems, even light icing could become critical. Training reflected these limitations. Many pilots of the era were skilled in handling aircraft visually. They could read terrain, anticipate wind patterns, and manage basic mechanical issues. But formalized training for instrument flight, flying solely by reference to cockpit instruments, was not yet standardized. The concept existed. Experiments demonstrated that controlled flight without visual reference was possible. But widespread adoption required trust in instruments that were, at the time, still evolving. Without that trust, pilots often relied on instinct. And instinct, in degraded visibility, could be misleading. Commercial aviation expanded despite these constraints. Airlines formed, routes established, schedules published. Aircraft carried mail across continents and passengers between cities. The demand for speed and efficiency grew steadily. With it, so did exposure to risk. Longer routes meant extended time in uncertain weather. Heavier aircraft required more precise handling. Increased traffic, even without centralized control, raised the potential for conflict. The 1930s became a decade of both growth and consequence. Accidents occurred with enough frequency to draw attention, but not yet enough understanding to fully explain them. Investigations were conducted, but methodologies were inconsistent. Data collection was limited. Flight recorders did not exist. Conclusions were often based on fragments, wreckage, weather reports, witness accounts. Patterns began to emerge, but slowly. By the onset of the 1940s, aviation entered another phase of transformation. The demands of the World War II accelerated technological development. Aircraft became faster, stronger, and more capable. Navigation systems improved under military necessity. Training programs expanded, introducing more rigorous standards. Instrument flying gained legitimacy. Pilots were trained to rely on gauges rather than sight. Procedures were formalized. Systems became more consistent. But this progress did not eliminate risk. It revealed it more clearly. The early decades of aviation were not defined by isolated failures. They were defined by a convergence of incomplete systems, each functional on its own, but not yet integrated into a cohesive structure of safety. Aircraft could fly. Pilots could navigate. Weather could be anticipated, but not reliably, not consistently, not together. It was within this environment that accidents occurred, not as anomalies, but as indicators. Each one exposed a gap in design, in training, in understanding, and each, in time, contributed to change. The accidents of early aviation did not originate from a single weakness. They emerged from the intersection of multiple limitations, each manageable in isolation, but unstable when combined. To understand a pattern, it is necessary to examine the system as it existed then, incomplete, evolving, and often inconsistent. Aircraft, structure without certainty. Early aircraft were functional, but not yet predictable. Design philosophies varied widely between manufacturers. There was no universal standard for structural stress tolerance, no long-term data on fatigue, and limited understanding of how repeated loads affected materials over time. Wood and fabric construction remained common through the 1920s. These aircraft were lightweight and efficient, but sensitive. Moisture could weaken joints. Fabric coverings could loosen or tear under strain. Small imperfections, barely visible, could propagate under flight loads. Metal aircraft introduced improvements. The Ford trim motor, with its all-metal structure, reduced some of these vulnerabilities. Corrugated aluminum skin added rigidity. Multiple engines provided redundancy. But new materials brought new uncertainties. Metal fatigue was not yet fully understood. Stress concentrations at joints and rivets could develop into fractures over time. Inspections were visual, often limited to surface-level checks. Internal weaknesses could go undetected. Engines, too, lacked consistency. Piston engines of the era were mechanically complex and prone to failure. Lubrication systems were less reliable. Cooling varied with altitude and airflow. A minor imbalance or overheating condition could escalate quickly. Multi-engine aircraft offered redundancy, but also complexity. Asymmetric thrust, when one engine failed, required precise control. Training for such scenarios was not yet standardized. Aircraft could remain airborne with degraded performance, but only if handled correctly. Crew, skill without standardization. Pilots of the early aviation era were capable. Many had backgrounds in military aviation, where adaptability was essential. They were accustomed to managing aircraft with limited instrumentation, relying heavily on visual cues and physical sensation. But formal training varied. There was no universal curriculum, no consistent certification standards across regions. Instruction often depended on individual experience rather than structured doctrine. Instrument flying represented a critical gap. Maintaining control without external reference requires trust in instruments, trust that must be learned and reinforced through repetition. In the 1920s and early 1930s, this training was minimal or absent for many pilots. The human body, in cloud, becomes unreliable. The vestibular system can misinterpret motion, creating false sensations of level flight or stable orientation. Without visual reference, a pilot may unknowingly enter a bank or descent. Correcting this requires disciplined reliance on instruments. But when those instruments are limited, or when training is incomplete, the correction may not occur. Crew coordination was also evolving. Multi-pilot operations were becoming more common, particularly in larger aircraft. But standardized communication protocols, role definitions, and workload management were not yet formalized. Tasks overlapped. Responsibilities blurred. In high workload situations, poor weather, navigation uncertainty, mechanical anomalies, this lack of structure increased the risk of error. Environment, weather without visibility. The environment presented challenges that were not yet fully understood. Weather forecasting in the early aviation era was broad and imprecise. Pilots often departed with general information, regional conditions, expected trends, but lacked detailed, real-time updates. Once airborne, they entered dynamic systems. Cloud formations developed and shifted. Visibility could degrade gradually or collapse without warning. Terrain, visible moments before, could disappear entirely. Fog was particularly hazardous. It formed close to the ground, obscuring landmarks and reducing depth perception. Approaches to landing became uncertain. Without instrument guidance, pilots relied on estimation. Icing introduced a less visible threat. Moisture in clouds, when combined with low temperatures, accumulated on aircraft surfaces. Wings lost aerodynamic efficiency. Control surfaces became less responsive. Weight increased. In aircraft without de-icing systems, even moderate icing could lead to loss of lift. Thunderstorms added another dimension. Updrafts and downdrafts could exceed the performance limits of early aircraft. Turbulence disrupted control. Lightning, while visually dramatic, was less significant than the structural stress imposed by violent air movement. Terrain compounded these risks. In regions with elevation changes, hills, mountains, uneven ground, navigation required precise altitude awareness. Without accurate charts or reliable instruments, maintaining safe clearance became uncertain. Systems, infrastructure and development, aviation systems, as a coordinated network, was still forming. Air traffic control, as understood today, did not yet exist. There were no radar systems to track aircraft positions, no centralized coordination to manage separation in real time. Flights operated independently. Departure times were staggered to reduce overlap, but once airborne, pilots relied on procedure rather than communication to maintain separation. Radio communication was emerging, but limited. Early radios were bulky, unreliable, and not universally installed. Signal range was restricted. Interference was common. In many cases, aircraft operated without continuous contact with ground stations. Navigation aids were in their infancy. Low-frequency radio ranges provided directional guidance, but required interpretation. Signals could be affected by terrain and atmospheric conditions. Coverage was incomplete, leaving large areas without support. Charts were improving, but not yet comprehensive. Topographical accuracy varied. Elevation data could be incomplete. Updates were infrequent. Maintenance systems lacked standardization. Inspection intervals were not always consistent. Documentation varied between operators. Knowledge of long-term wear patterns was still developing. Accident investigation, as a formal discipline, was limited. Without flight data recorders, analysis depended on physical evidence and reconstruction. Conclusions were often cautious, sometimes inconclusive. Yet, even within these constraints, patterns began to emerge, not from single events, but from repetition. Aircraft entering cloud without adequate instrumentation. Pilots misinterpreting orientation. Weather conditions exceeding expectations. Systems failing to provide timely support. Each element, on its own, was manageable. Together, they formed a chain. In the early decades of aviation, safety was not yet a system. It was a collection of parts: aircraft, crew, environment, and infrastructure, each advancing at a different pace. Where those advances aligned, flight was successful. Where they did not, the margins narrowed. And within those margins, accidents took shape. There is no single accident that defines the early decades of aviation. There are many, different locations, different aircraft, different crews. Yet the structure of failure, when examined closely, often follows a familiar progression, not abrupt, not chaotic, but incremental, a sequence of small, manageable deviations, until they are no longer manageable. Accident I, loss of reference. The aircraft departs under acceptable conditions. Visibility is sufficient. The route is known. Navigation is based on landmarks, rail lines, rivers, terrain features that provide orientation. The flight proceeds without difficulty. At altitude, cloud begins to form ahead. Not a solid barrier, but scattered layers. Gaps remain. The pilot continues, expecting to maintain visual contact with the ground through openings in the cloud. Gradually, those openings close. The aircraft enters a region of reduced visibility. The ground becomes indistinct, then disappears entirely. Inside the cockpit, the instruments offer limited guidance. A compass, slow to respond. An altimeter, indicating height but not trend. No artificial horizon. No directional gyroscope capable of stabilizing orientation. The pilot attempts to maintain level flight, but without external reference, subtle deviations begin. A slight bank develops. It is not immediately apparent. The body perceives stability. The aircraft, however, begins a shallow turn. The nose lowers slightly, increasing airspeed. The altimeter begins to unwind. At first, the change is gradual, easy to overlook. The aircraft continues descending. Without visual cues, the pilot relies on sensation, correcting based on perceived motion rather than measured attitude. These corrections, though well-intentioned, are inaccurate. The bank angle increases. The descent steepens. Terrain, obscured by cloud, rises beneath. There is no warning, no terrain awareness system, no radio guidance, only diminishing altitude and increasing speed. Recovery requires recognition. Recognition requires reliable reference. Neither is present. The aircraft continues its path until the margin between altitude and terrain is no longer sufficient. Accident 2. Weather and icing. The flight begins in stable air. Temperature is low but within expected limits. Cloud layers are present, but not considered hazardous. The aircraft climbs into a region where moisture and temperature intersect. Ice begins to form. At first, it is subtle, a thin layer along the leading edge of the wings. Barely visible, the aircraft continues to perform within acceptable parameters. Lift is reduced incrementally. Drag increases. Engine power remains constant, but the aircraft requires more of it to maintain altitude. The pilot adjusts throttle. The aircraft stabilizes temporarily. As the flight continues through cloud, ice accumulates further. Control response becomes less precise. The aircraft feels heavier. The airspeed indicator shows a gradual decrease, despite increased engine output. This is not immediately recognized as critical. Icing, at this stage in aviation, is not fully understood. There are no de-icing systems installed. No standardized procedures for avoidance beyond general caution. The aircraft begins to lose altitude. The pilot increases power again, attempting to compensate. But the aerodynamic profile of the wing has changed. Lift cannot be restored through power alone. The descent continues. Control inputs produce delayed responses. The margin between control flight and stall narrows. At a critical point, the wing can no longer sustain lift. The aircraft enters an aerodynamic stall, not abrupt, but progressive. Altitude is insufficient for recovery. Accident 3. Navigation and terrain. The route crosses unfamiliar terrain. Charts provide general guidance, but lack detailed elevation data. The aircraft maintains a planned altitude, calculated to ensure safe clearance based on available information. Weather conditions deteriorate en route. Visibility decreases. Landmarks become difficult to identify. Dead reckoning becomes a primary method of navigation, estimating position based on heading, speed, and elapsed time. Wind conditions differ from forecast. A slight drift develops. Over time, this drift compounds. The aircraft deviates from its intended path. The terrain below is no longer consistent with expectation. Elevation increases gradually. Hills become ridges. Ridges become higher ground. But without visual confirmation, the change is not immediately apparent. The altimeter indicates stable altitude, but altitude alone does not guarantee clearance. Terrain elevation is rising. The margin between aircraft and ground is narrowing. Without accurate positional awareness, the pilot cannot adjust effectively. Cloud obscures the landscape. There is no visual warning of proximity. No system to indicate terrain ahead. The aircraft continues forward, maintaining altitude relative to sea level, but not relative to the ground beneath. At a certain point, the two converge. A common structure. These accidents differ in detail, but their structure aligns. Each begins with conditions that are manageable. Each involves systems that function, but not completely. Each progresses through small deviations, subtle incremental, often unnoticed until they accumulate. There is no single point of failure, no dramatic moment where outcome becomes inevitable. Instead, there is a gradual erosion of margin. Visibility reduces, control degrades, position becomes uncertain, altitude becomes insufficient, and within that narrowing space, the outcome is determined. In the early decades of aviation, the turning point was rarely a sudden event. It was a transition, from known to unknown, from control to uncertain, from margin to none. In the early decades of aviation, accidents did not end with impact. They began again, quietly, on the ground. There were no flight data recorders, no cockpit voice recordings, no digital traces of altitude, speed, or control inputs preserved in memory. What remained was physical. Wreckage scattered across terrain, fragments of structure, engines displaced from their mounts, instruments frozen at their final indications, sometimes reliable, often misleading. Investigators worked with what they could see and what they could infer. Reconstruction without record. The process was methodical but limited. Investigators examined debris patterns to determine angle of impact. They assessed structural integrity to distinguish between in-flight failure and ground collision damage. Engine components were inspected for signs of operation, rotational scoring, heat distortion, fuel presence. But these clues were incomplete. A broken wing could indicate structural failure, or it could be the result of impact forces. An engine at idle could suggest power loss, or simply throttle position at the moment of collision. Without recorded data, certainty was difficult. Conclusions were often cautious, probable causes, rather than definitive ones. Yet even within these limitations, patterns began to form. Emergence of systemic thinking. Early investigations were initially focused on individual events. What happened here, to this aircraft, on this flight? But as accidents accumulated, similarities became difficult to ignore. Aircraft entering cloud and failing to maintain control. Flights encountering weather beyond their capability. Navigation errors leading to terrain impact. These were not isolated anomalies. They were recurring structures. Gradually, the focus shifted from singular blame to systemic understanding. Not just what failed, but why similar failures kept occurring. This shift marked the beginning of modern accident analysis. Regulation begins to form. Governments and aviation authorities began to respond. In the United States, the Civil Aeronautics Authority was created to bring oversight to a rapidly expanding industry. In the United Kingdom, similar responsibilities were managed through evolving regulatory bodies that would later consolidate under the Civil Aviation Authority. These organizations introduced structure where there had been variation, certification standards for aircraft, licensing requirements for pilots, defined maintenance procedures. Airworthiness became a measurable concept, not absolute, but consistent. Aircraft were no longer evaluated solely by their ability to fly, but by their ability to fly reliably over time. Instrument flight, from concept to standard. One of the most significant changes emerged from repeated accidents involving loss of visual reference. Instrument flying, once experimental, became essential. The work of pioneers like Jimmy Doolittle demonstrated that controlled flight using instruments alone was not only possible, but practical. Training programs began to incorporate these techniques. Pilots were taught to trust instruments over sensation, to maintain attitude using artificial horizons, to interpret directional gyros with consistency, to monitor altitude trends rather than static readings. This transition was not immediate. It required new equipment, new procedures, and a cultural shift from instinctive flying to disciplined interpretation. But over time, it reduced one of the most persistent risks in early aviation. Navigation systems improve. Radio navigation advanced rapidly in response to need. Low-frequency radio ranges expanded coverage, providing structured airways that pilots could follow even without visual reference. Signals became more reliable. Interpretation became standardized. Air routes were no longer defined solely by geography. They were defined by signals. Aircraft could navigate through cloud with greater precision. Drift could be detected and corrected. Position could be estimated with increasing accuracy. Charts improved alongside these systems. Topographical data became more detailed. Elevation information more precise. Updates more frequent. Navigation, once an estimation, became a discipline. Weather, from unknown to managed risk. Meteorology advanced in parallel. Observation networks expanded. Weather stations provided more frequent data. Forecasting methods improved, incorporating broader patterns and localized conditions. Pilots received more detailed briefings before departure. In-flight updates, though still limited, became more accessible through radio communication. Icing, once poorly understood, became a recognized hazard. Procedures were developed to avoid known icing conditions. Aircraft began to incorporate de-icing equipment, boots on leading edges, heated surfaces, systems designed to preserve aerodynamic integrity. Weather could not be controlled, but it could be anticipated and, increasingly, avoided. Air traffic control emerges. Perhaps the most transformative development was a gradual emergence of coordinated air traffic control. Initially, this was procedural. Scheduled departures, defined routes, altitude separation. Over time, it became active. Ground stations communicated with aircraft. Positions were reported. Clearances were issued. Separation became managed, not assumed. The sky, once open and unstructured, began to take on form. Maintenance and engineering discipline. Accidents involving mechanical failure led to deeper examination of materials and design. Metal fatigue, once an abstract concept, became measurable. Inspection techniques improved. Maintenance intervals were standardized. Engineering moved from reactive repair to preventative analysis. Aircraft were not only built to fly, they were built to endure. From incident to instruction, each accident contributed incrementally, not always immediately, not always completely understood, but over time, the accumulation of evidence-shaped practice. Procedures were written, checklists developed, training standardized. The industry began to learn, not from theory alone, but from consequence. The aftermath of early aviation accidents was not defined by rapid resolution. It was defined by gradual understanding. A shift from isolated interpretation to systemic awareness. From individual error to structural limitation. From uncertainty to method. The aircraft of the early 20th century were not inherently unsafe. They were incomplete. They represented a stage in a process, one that had not yet integrated knowledge, technology, and procedure into a unified system. Each component existed, but not yet in alignment, and it was within that misalignment that accidents occurred. By the mid-20th century, the pattern had become clear. Controlled flight into terrain was no longer viewed as an isolated misjudgment, but as a failure of situational awareness, often compounded by inadequate navigation and insufficient instrumentation. Weather-related accidents were no longer attributed solely to unpredictability, but to limitations in forecasting, communication, and avoidance procedures. Mechanical failures were no longer accepted as unavoidable, but as indicators of design limits, maintenance gaps, and material behavior that required deeper understanding. The shift was subtle, but fundamental, from acceptance to analysis, from reaction to prevention. Instrument flight became standard. Aircraft were equipped with reliable attitude indicators, directional gyros, and redundant systems designed to provide consistent reference, regardless of external visibility. Pilots were trained not only to operate these instruments, but to depend on them. The horizon, once a visual necessity, became optional. Navigation evolved into precision. Radio beacons expanded into networks. Airways were defined not by what could be seen, but by what could be measured. Position became verifiable. Drift became correctable. Uncertainty narrowed. Air traffic control matured. What began as procedural separation developed into active management. Radar, introduced later, would transform this further. But even before its widespread use, the concept of monitored airspace reshaped flight operations. Aircraft no longer moved independently through open sky. They moved within a system. Engineering advanced with consequence in mind. Metal fatigue was studied, quantified, and incorporated into design limits. Redundancy became intentional. Critical systems were duplicated, not as a precaution, but as a requirement. Maintenance became structured. Inspection intervals were defined. Documentation standardized. Failure, when it occurred, was analyzed not only for cause, but for prevention. Weather, once an external force beyond control, became a managed variable. Forecasting improved. Reporting expanded. Pilots gained access to real-time updates, allowing decisions to be made with greater clarity. Icing, turbulence, storm systems, each became part of operational planning rather than unforeseen obstacles. Risk remained, but it became measurable. Perhaps the most significant change was not technological. It was philosophical. Early aviation accepted uncertainty as inherent. Later aviation sought to reduce it. This shift required more than equipment. It required discipline. Standard operating procedures, checklists, training frameworks that emphasize consistency over improvisation. Individual skill remained important, but it was no longer the sole defense. Safety became systemic. The accidents of the 1920s through 1940s did not disappear without trace. They informed. Each one contributed, incrementally, to a body of knowledge that reshaped aviation. Not immediately, not without repetition, but steadily. Lessons were written into procedures. Limitations were addressed through design. Unknowns were studied until they became understood. Modern aviation operates with a level of reliability that would have been difficult to imagine in those early years. Aircraft navigate across continents with precision measured in meters. Pilots operate within structured systems supported by continuous communication. Weather is tracked, modeled, and integrated into every phase of flight. And yet, the foundation of that reliability is not technological alone. It is historical. The early accidents remain part of that foundation, not as isolated events, but as indicators of what was missing. They define the distance between what aviation was and what it became. There is no single moment where aviation became safe, only a gradual transition, from uncertainty to structure, from limitation to integration, from experience to system. The horizon, once uncertain, is now defined, not by sight, but by understanding.